Alright, so processes not only share the CPU cores, they of course must also share the system memory. It's the OS's job to regulate the process's use of memory to ensure that each process doesn't interfere with the portions of memory used by other processes and by the OS itself. Here, for example, the processes A, B, and C have been allocated their own portions of system memory. While the OS may access any portion of memory as it chooses, because the OS is supposed to be in charge of the system, each process can only access its own portion of memory. As we will explain shortly, this restriction is enforced by the hardware, making it impossible for a process to mess with addresses outside of its own portion of memory. However, we need a loophole for this restriction because processes must be able to invoke certain routines at fixed addresses in the OS's portion of memory. These routines, called system calls, are the means by which processes initiate requests to the operating system. These system calls provide functionality for things like, say, reading and writing files, or for sending and receiving data over the network. To invoke a system call, a process must use a specific CPU instruction, usually called syscall, in which the process specifies a system call number. When this instruction is invoked, the processor looks in the system called table for the address of the routine corresponding to the number and jumps execution to that address. As an example, if you are familiar with C, which by the way was a requirement for taking this course, you might have used the function fopen. Fopen takes two parameters. The first one is a C string containing the name of the file to be opened, and the second one is also a C string containing a file access mode. The fopen method in C is a library function that is used to open a file to perform various operations which include reading, writing, etc. along with various modes. If the file exists, then the particular file is opened as a new file is created. So fopen is a function from C library that internally performs one or more system calls. Let's suppose that process A is the code that you see here. Now, fopen will make a system call to the underlying OS in order to tell the operating system that process A requests a file under the name demo_file.txt. All your files are stored in your hard drive memory, so the operating system will go and grab demo_file.txt from the hard drive and return it to process A, which is stored in the RAM. Now, this might be confusing for some, but fopen does not directly invoke a system call. Fopen is just a wrapper function for a system call called open. The wrapper functions, which is fopen in this case provided by the standard library, provides some extra feature and or sanity checking, error checking for the underlying system call. If you go inside the implementation of fopen, you will see towards the end that invokes the open, which is a system call. Again, system calls are the bare minimum calls that is passed to the kernel, which executes in kernel mode and returns the required result to the user space application, which is process A in this case. The same thing for fprintf. Fprintf is just a wrapper function that will ultimately use write to write anything on a peripheral, whatever is the kind of device you write on. Write is designed to only write a sequence of bytes. That's all and nothing more. But as write is considered too basic, you may want to write an integer in 10 bases or a float number in scientific notation, etc. Different libraries are provided to you by different kind of programming environments to ease you. For example, the C programming language gives you fprintf that lets you write data in many different formats. So you can understand fprintf as a function that converts your data into a formatted sequence of bytes and that calls write to write those bytes onto the output. But C++ gives you cout, Java, systemout, println, etc. Each of these functions ends to a call to write, at least on POSIX systems. Another example using a diagram this time is fwrite. The following diagram shows the sequence of steps involved in calling one of the basic functions of the C standard library, which is fwrite. But note, this is simplified a bit for clarity. So here are the steps that the process involves. First, fwrite, together with the rest of the C standard library, is implemented in GNU C library, which is one of the core components of the Linux operating system. Fwrite is essentially a wrapper for the write library call, and write will load the system call ID, which is 1 for write, and arguments into the processor registers, and then cause the processor to switch to kernel level. The way this is done depends on the processor architecture, and sometimes on the processor model. For example, on x86 processors usually call interrupt 80, while x64 processors use the syscall processor instruction. Then the processor, now executing in kernel space, feeds the system call ID to the syscall table, extracts the function pointer at offset 1 and calls it. This function, which is syswrite, is the kernel implementation of writing a file. Because the operating system controls the system call table, a process can only jump execution to addresses of the operating system choosing. So aside from this loophole, how do the operating system and hardware restrict the process to only access its own portion of memory? Well, first off, the CPU actually runs in two different privilege levels. When OS code runs, the CPU is put into a privilege level that allows access of the I/O devices and any address of memory. When a process runs, however, the CPU is put into a privilege level that triggers a hardware exception when the code attempts to directly access the I/O devices or addresses not allowed for that process. Processes are supposed to directly touch only their own memory, not anything else in the system. Now, to understand how the CPU knows which addresses are allowed for each process, we have to first look at how a process uses memory. Each process uses a portion of its memory for a stack, for a heap, and for storing the process's code itself in a section confusingly called the text section, even though the code is in binary form. The code section is straightforward. The binary instructions are stored in a contiguous chunk of memory and never modified for the duration of the process. The stack and heap, though, are both for storing data. The difference is that the stack stores the local variables used by the process, and the heap stores everything else.